Okay, so this week we're going to talk about groundwater. And so, like some of the other topics we've covered, there's a little intro here where we have to learn some basics of groundwater, and then we can go into the hazards that are related to groundwater and then some of the solutions. So I will try to be fast and furious without being too confusing. No guarantees. You can always pause and take a break if this thing runs kind of long, and you can take it in little pieces. So what we want to look at when we look at groundwater is first to understand how it relates to all the other, areas of water that we're kind of aware of. And so when we rank our amounts, we can certainly come to the agreement that oceans are the most volume of water that we have on the planet. And as we rank the others, glaciers, at least currently, are next. But then it might be surprising to you that groundwater is the third largest by volume. So it's more than streams and lakes combined. And then, of course, we have the atmosphere and biosphere. And so if we take out our oceans, which we aren't talking about because they're not fresh water, so the streams and lakes and the groundwater and atmosphere, these are fresh water and not salt water. So if we kind of look at fresh water, so now we've removed our lovely oceans here, you can see that obviously there's a lot of water, fresh water, in ice sheets and glaciers, so Antarctica and Greenland and things like that, and some of the mountain glaciers. But you can see that groundwater compared to lakes and reservoirs is pretty huge. And so the reason that you're probably not aware of that, of course, because it's in the ground. We really don't see it. And so we're accessing the water from the ground by drilling into the ground and pumping it up. So just like we would do an oil well, we're doing that with water. And the water's being stored in the rock or sediment, and then we can access it and then pull it out of the ground. And so it's a big source of fresh water. And certainly for us here in Arizona, it plays a big role because we don't get a lot of moisture. You guys haven't been aware, we don't get much rain here. We do live in a desert, by the way, so we need the groundwater. And so we do use it, of course, to supplement our water. And, in a lot of places, groundwater is providing at least 50%. And that's true here in Arizona. So the water that you use, we have the reservoirs, of course, and that's rainwater that's been stored, captured, things from rivers. But the things that sink into the ground, we're pulling a lot of water out of the ground to supplement our water so that we can all live here and be happy. So, of course, we care about water and groundwater because we use it. We use, so much of it. So we want to be aware of where it is and so that it's not getting contaminated. There is some issues, some hazards. Sinkholes is probably one of the more dramatic issues that can occur from groundwater problems. We don't have that many issues with sinkholes here, though if you lived in Florida, the sinkhole capital of the world, you might be a little concerned about that. So just as a general rule to kind of understand how the hydrologic cycle works, right? So evaporation pulls water from the sea, right? It evaporates, it gets up in the atmosphere, it moves about, and then it condenses back to water, it falls to the ground, hits the ground. And of course, when it hits the ground and goes its crazy ways, like last time we talked about flooding. So that is the water that hit the surface and moved into rivers and streams. We don't want to talk about that this week. We want to talk about the water that actually penetrates into the ground and gets stored there. And so this is the groundwater that we want to focus on. And of course, the cycle is that it moves and it can be, taken out and then replenished and things like that. So when we look at groundwater, there's a few little terms or areas we want to define. So what we're calling the groundwater or the water table is a kind of an imaginary line that we could draw. And the idea is that as water hits the surface and sinks in, it is moving between the open spaces here. So the open spaces can be from a lot of reasons. One is that it can just be that there is just dirt on the ground or sand or gravel. And of course, those pieces do not fit together perfectly. So there is space, and it's space that the water can move through. And so it'll percolate down into and through these spaces, and it'll keep sinking until it reaches some boundary. And that boundary can be a couple things. It could be a solid rock layer that does not have any pore spaces or open spaces in it, so the water can't penetrate. And so it stops there and it starts to fill up all the open spaces that are available. We pour more water in, it fills up more of those open spaces. And this boundary between where all the open spaces are full and all of the open spaces are not is what we're calling the water table. Okay, so it's just this boundary between where full, not full, right? And so when we drill into the ground here, what we see from our well is that water will fill up our well to the elevation of the water table. And how's that working here? Well, of course, when we drill a well, we put a pipe down here, but the pipe that's deeper here is perforated. It's got holes in it so that the water can move into the pipe and fill it up. And like I said, it'll fill it to the level of this imaginary line that we're defining by the open and non-open spaces, right, full of water. Okay? And this kind of points out another thing I'll talk about later, but what we tend to see for what does the water table look like and how deep is it, and that's based on climate and things like that. If you're in a place that gets a lot of rain, we can fill up the ground pretty fast, right? And it can be closer to the surface. Here in Arizona, we don't have a lot of moisture and we're a little higher elevation, so our groundwater table is pretty low, a couple hundred feet maybe. But it tends to mimic the land surface. So the idea would be that if we were here and we wanted to find out where the water table was, we would drill down. If we went up here on the slope, the groundwater table is not straight across. It's going to mimic the land surface. So we have this kind of slope and then flat. The groundwater table is going to be sloped and flat. And that's a very general rule, but it gives us some information about how deep the water might be in certain locations. So we can use that to our advantage. So when we talk about groundwater, one of the big things that we want to focus on is porosity. So that is just the amount of open spaces in rock or sediment. So we talked about sedimentary rocks in the past briefly, and we said that, you take a bunch of pieces and you dump them somewhere, you squish them, and we glue them together. If there's a rock, yes, there's sediment holding some of these pieces together, but there's still some open spaces. And so rock can absorb water. Not all rock, right? Certain rock types, sandstones, limestones, conglomerates, these rocks have the ability to store water. Because even though we look at it, it looks like a solid, there is some air in there, open space. And as long as they're connective open spaces, I can store some water in there. Now, if it's just sediment, it's a lot easier to store the water because there's no cement. So I know that there's a lot of open space there because my little fragments of pieces don't fit together perfectly. Right? So we would identify it as a high porosity material if a lot of the pieces are the same size, there's no cementation, or if the rock is highly fractured, because remember, cracks in the rock are open space and they can store and move water. So high porosity materials are well sorted, no cement, are fractured. Low porosity materials are if they're poorly sorted, which means big and small, because the small stuff is taking up some of my open space. If it's really well cemented, that's taking up some of my open space, and massive just means not fractured. So we want these things, high porosity, because we want to store as much water as possible. This is important when we talk about getting water from the ground and things like that. And so when we look at porosity, sands and gravels, so like beach sand, things like that, loose stuff that's not cemented, make great what we're going to end up defining as an aquifer, which is material that can store and move water. And so sandstones, fractured rocks, even pumice has a high porosity, although we'll come back to that as why it might not be a good aquifer. Non-porous materials are massive rocks, no fractures. Granites, things like that, there's no open space there, so we can't. Evaporites, negative. They're crystals that are grown together. There's no open space there. So those are not good materials / rocks for storage and transportation of water. So we need our second factor, besides porosity, we need what's called permeability. And in general, we're just going to say that it's the ability of the water to move through the open spaces, or we would say how well connected are the pore spaces or the open spaces. If they're very well connected, it has a high permeability. We like that. We want our rocks or sediment to have a high porosity and a high permeability. Because look, we could look at something and say, wow, there's a lot of storage there, a lot of open space. But if it's not connected, it means it can't flow, which means I can't suck it out of the ground. Because, and of course, it can't even get into the deeper holes in my rock because the water can't penetrate because it can't connect. And so we'll go back to that little picture of a pumice, which is a volcanic rock with lots of holes in it. Because the way the holes are made, they're usually not very well connected. So although we'd look at a pumice and say that is a high porosity, it has a super low permeability. It makes it a crappy storer and mover of water. Is not a good aquifer, right? We want sands, gravels, sandstones, limestones, or highly fractured rock because they have both porosity and permeability. We like that. That is good. And the term we're giving to these materials are aquifers, rocks or sediment that can store and transfer water. If it can't do that, we call them aquicludes, which means the water can't get into them. So granites, evaporites, rocks that aren't fractured, don't have a lot of porosity, or have no permeability or no porosity, are called aquicludes. Water can't move through those things. Okay, so what does our water table look like? We said it's a subdued copy of the land surface. And so if you have the land surface that's kind of up and down like this, right, you get a kind of arcing here because that's what the surface is doing. Now, of course, this image here is not Arizona, and that's because we don't have a water table this high because of our climate. And so in places back east, the water from the groundwater, is actually flowing into lakes and streams and adding some water to it over time. Here in Arizona, we don't get that. We actually get a loss of the streams and lakes into the ground because our groundwater table is low. So it looks something like this. So here in Arizona, we're down here. So streams and lakes actually lose material to the ground, whereas in places where the groundwater table is a lot higher, it's actually adding to that. So we call them losing or gaining streams instead of using the effluent, influent, because I can never remember those either. So a gaining stream means it's gaining water from the groundwater. Losing stream, it's losing water to the groundwater table. Okay, other ways we can get water to kind of intersect the surface is through springs or seeps. And that is places where the material is penetrating the ground. It's porous and permeable, so it can move. But in places where we have a sharp change in elevation, the water and the fractures can make it to the surface here, and we can get seeps or little springs come out. Faults are places where we can get springs and things like that. Sometimes in limestones where we have caverns and things like that, we can get springs. So it's anywhere where the water table is intersecting the surface. This is an example in the Grand Canyon. So the big canyon has carved through the rock and intersected some of the water tables there, and so we get big springs there. So how does groundwater move? And you're like, what? I didn't know groundwater. Okay, groundwater's moving. So in the ground, the water is actually flowing. And just like if it was on the surface, it's going to flow from high to low. Now, it doesn't have to be extreme. In the example here on the left, there's this little hill here. What that means is water that's in the ground that's right here is actually flowing to the right, down toward the stream. Water over here on the left is actually flowing in the other direction. Now, it's not obviously moving like it would on the surface because it's working its way through these maze, right, of open spaces that are connected. And so it might move, it might move, I don't know, a mile a year, right? So it depends on the gradient, which is how steep is the slope here. And of course, how well connected everything is, right? So if it's well connected, it can move easily, that'll increase its speed. If it's steeper, that'll increase its speed. And so the velocity really depends on the slope. So we talked about the gradient is a term we use for slope, and the permeability. So those two things can dictate how fast the water is moving in the ground. Okay, so if we're to give you something like this, what the hell is this, you say? Okay, this is a map, let's say, of the surface. And what you're seeing in parentheses is elevations above sea level. So think of this like a topographic map. And so way back when we talked about topography, and we said what we could do is we could map the surface of the earth by connecting points of equal elevation. But if we drill a well into the ground, and the water in the ground will flow into my well and fill it up to the level of the water table, I can use that elevation. And then if I have all these wells with the elevation of the water table, I could treat that just like the surface of the earth, and I could make a topographic map of the water table. Where is the water table higher? Where is it lower? And so in general, if we looked at this map, and this is elevations of the water table, we can see that the numbers are certainly higher to the upper right here. And the lowest points as we look around would be to the lower left here. That would be an indication that the movement of the water, just like if it was on the surface, is going to flow from high to low. So there's some general movement of the water from upper right here to lower left. And how we would do that specifically is just like if we were creating a contour map of the surface, we would connect points of equal elevation. So that's what this thing has done really quickly. The blue are contour lines, but they are contour lines of the groundwater table and not the surface of the earth. And so 960, 960, 960, 960, those are all connected. The 70s, the 950s, 940s, you get the idea. Now, the other thing that we do, and if we were going to get into groundwater modeling and everything, we could get more complicated, but the idea is that you can draw what are called flow lines. And what are flow lines is just the direction that the water is moving in the subsurface based on the elevations of the water table. Once we connect points of equal elevation and make a map, a topo map of the groundwater table, we could then draw lines. And specifically, you draw lines that are perpendicular to the contour lines you have drawn. And so here, because they're all going this way, if water hits the ground here and sinks down to the groundwater table and hits that, the water in the ground is actually flowing perpendicular. So it's flowing directly like this. If I was to put a drop of water right here, it would not flow to this point. And that is because it's going to flow and cross the contour lines perpendicular. So water here is actually going to flow down in this direction. And that is only based on the fact that the elevations of the water table have moved around and changed the direction of my contour lines. Okay, so we can be pretty specific about how things flow. So let me give you a broader view. So here's a map of part of the valley here. Here's South Mountain and the Phoenix Mountains. These are contour lines of the water table. So they're very generic, very general. But we could draw lines that show us the flow. Water that falls up here, where my cursor is, would flow down this way and be drawn perpendicular to the lines here as it moved, right? If it was over here, it would actually flow down this way and then turn and come over here. And so the idea is we can use the contour of the water table to predict where water's moving. And so when we talk about issues with groundwater, one of those is pollution. And so if I know what direction the water's moving, I can find out where the pollution is coming from. So let's argue that you have your dream house right here, and you find that there is pollution in your well that you've drilled around your house. And we want to figure out who is doing it. Where is it coming from? And so if we have some candidates for our, people that are polluting our groundwater, if we knew nothing about groundwater, we might argue that we could never tell. They're all about the same distance away. Could be anybody. But look, because you know something about how groundwater behaves in the subsurface, this company cannot be polluting your, because look, they're down here in the 900s. In order for their water to get up here to pollute your well, they'd have to go up in elevation. That is not how groundwater moves. It moves just like on the surface, from high to low. And so those guys, they're anything they're dumping in the ground is going this way because it's going from high to low and it's crossing their contour lines perpendicular. Okay? So then if we look at somebody else, we look at this. If they put it in here, why does it go here? It doesn't. We're going to argue that when we draw our flow lines, they must cross the contours we've drawn perpendicular. And so that makes its path something like this. It's going to bypass your house. But this company up here is above an elevation, and when I draw my flow lines, they come right by your house, and we can predict who the polluter is. This is it's a pretty basic concept for groundwater, but it's huge when it comes to groundwater remediation, because we find where the water pollution is and we backtrack and figure out where's it coming from. And we can use just the slope and elevations of the water table because we have wells everywhere. There's hundreds of wells throughout the valley, and we can get that data and we can draw these little models of the groundwater table. Okay, so just to give you an idea how we're lucky here in the valley, we're a big bowl, and so we've got a lot of mountains we know that are around here, South Mountain, Australia Mountains, Phoenix Mountains, all those kind of good things. But we have basins in between, right? We are called the Basin and Range Province because of this. And so I know these numbers are really hard to read, but this is thickness of sediment, how thick the sediment is here. And in some places it says greater than 10,000 feet, or unknown in some cases. And so there's thousands of feet of sediment that have piled into the basins over the millions of years the valley has been developing. And so that material has the ability to store some water. This is where we're getting a lot of our groundwater from. And because it's so thick and it's taken millions of years for the water to get in there, there's a lot of water there. Now, not all of it is awesome and we can access it, but if we were to look at this is a cross section, and it's kind of from Apache Junction out to Luke. And it's a little exaggerated for elevation just to give you an idea, but here's a big basin. And then here's some bedrock, and here's another big basin. And so we've got these different materials, right? So we got units, the lower unit, a middle unit, and an upper unit. They have different properties. They store water better or worse in some places. And so I drill into the ground and I can pull some water up because I have water stored here. Now right here, not so good because I don't have a lot of sediment, so there's not a lot of water stored here. But other places I can drill into these areas and pull up water, right? Very useful. All right, what else have I got for her? And then, we could talk about where's the water flowing to. We could draw lines all over the place here and figure out the general flow. If we got really detailed, we can get down into Scottsdale area and just look at the general flow in that particular area. Okay, what else we want to talk about? So just a few other terms. There is something called confined aquifers. So aquifers that are unconfined mean that as I dump water into the ground, it flows right into the aquifer. There's nothing blocking it. A confined aquifer means that there is a layer above and below, which is confining the material that's storing the water. So how the heck does the water get in there? Well, it's typically something like this, where we have tilted layers here. And this porous and permeable layer is exposed somewhere where water can access that. So it gets into here, it moves down into this layer that is both permeable and porous, so it can store and transmit water, and is confined. So if you've ever heard the term artesian well, like, hey, I got you some artesian water and it's very special, it's really not. All an artesian well is, based on how this is being deposited, the water into this layer, the elevation of the water table is technically up here when this layer here is full of water. Which means if I take that out into this valley here, the water table elevation is really above the ground level here. So if I take a well and drill into it and puncture into this, we said that the water would flow into my well and go to the elevation of the water table. So that means that it would actually come up through my well and kind of just shoot out of the ground of its own. I wouldn't have to pump it out. It'd come up on its own. This is kind of how, you see pictures of people drilling into oil wells, and it's a gusher, right? Comes up because there's pressure there, right? So that's what an artesian well is, and that's what a confined aquifer is. What else I got for you? So look, one of the things we want to do, of course, because groundwater it's renewable, but it's slow. And so we would argue that we take water out, we can put some back in, it'll come naturally when it rains, but in some places we take more out than we put back in. And so one of the big challenges for groundwater is to manage the withdrawal with the recharge, and that's not always something that we do well, and so we can run into problems with water issues for sure. So let's see, okay, it's getting long. I'm going to pause it here because that was kind of the gory details of groundwater, how it works, how it flows, and some of the terminology, and then I'll make a quick video about some of the issues and some of the solutions.